Hello, my name is Kyle, and this is lab report number 3. So to start off, I'll introduce the lab. This lab focused on an object moving through space and the effect that gravitational forces can have on its position, velocity, net force, and momentum. Main result from part 1 was an elliptical orbit that didn't crash into a black hole. The main result for part 2 was a spaceship was able to avoid crashing into the black hole and a circular orbit from the planet. In performing the experiment, we're looking to verify the accuracy of Newton's second law and explore the idea of net forces acting upon an object in motion. So some of the equations we used are velocity update, position update, gravity force formula, and the force momentum equation. So here is the process of what we did. So we used the starter code and glow script, and then got our random star trajectory, set our initial conditions, and then we edited the variables in order to make the code run properly. And then once you got the list of values for mass at the end, you average them to get a singular value. Then for part 2, you do a similar thing. You set up the glow script code, fill in the initial conditions, enter the mass you got from part 1, and then once you run it, you change around the initial velocity in order to avoid crashing into the black hole. Some of the assumptions we made while running the experiment are that the only forces acting upon all 3 objects were the other 2 objects, and that we didn't consider the drag while in the atmosphere of the planet. And for part 1, it's important to note that the systems were the planet and the black hole, and in part 2, you have 3 systems, the black hole, the planet, and the ship, in terms of how they interacted with each other. The initial conditions you can see listed here on the left, and then the code is for it on the right. Here are some of the update formulas for computational models. For our computational models, we used a velocity update formula. You can see the code right here. We plug in dp/dt for fnet in order to solve for it. Position update formula, we just plug in our position with our average velocity times time. And then the momentum equations, you can see how we broke down momentum and fnet into their, or dp/dt and fnet into their parallel and perpendicular components. Here's the code for part 1 and part 2. Part 1 code, you can see we start with the momentum, initial and final. You get the change in velocity, change in momentum. You get dp/dt, and fnet is equal to dp/dt, so you set it equal there. Then when you break it down into components, you can see you can get dp/dt parallel and dp/dt perpendicular, which also gives you fnet parallel and perpendicular. And then you can solve for the mass of the ship, and then, or the black hole, sorry. And then in part 2, you can see that we used the gravitational force equations in order to get the forces for each of these things on each other, and then for the force, or the net force on each object, you combine the forces acting upon it. And then testing around with that, you can get the initial velocity. So here's the glow script results. For part 1, you see the elliptical orbit. For part 2, you can see it avoiding the black hole. Some potential errors and improvements. An error in this lab is that taking the average mass of a bunch of values and then using it as a singular mass for the black hole could lead to some rounding errors and potential for mistakes. And then, yeah. So what does it mean? The net force, how is the net force and its parallel and perpendicular components different from the rate of change? So of momentum and its parallel and perpendicular components. So the net force of the object is solved for by taking the change in momentum over the change in time, which you can see in this equation below. And this is basically just proving how dp/dt is equal to fnet. And then we can break it down into the components, as you can see on the bottom. Fnet is going to equal the parallel components of fnet plus the perpendicular component of fnet. And if we know that fnet equals dp/dt, dp/dt is also going to equal its parallel plus perpendicular components. We're able to see that the parallel component of fnet is equal to the parallel component of dp/dt, and the perpendicular component of fnet is equal to the perpendicular component of dp/dt. For the what if, what initial velocity would your spaceship need in order to enter into some kind of orbit around the black hole? By severely decreasing the speed in the x direction and severely increasing the speed in the y direction, the ship is able to avoid getting thrown out of the orbit, which you can see here. On the left, it's where it gets thrown out of orbit, and on the right, you can see it's actually following a steady orbit along with the planets. Yeah, that is basically all I had for my lab. Thank you for watching.